This is a quick video to demonstrate interfacing a Nintendo Wii Nunchuk to a Microchip PIC Microcontroller. Looking at the hardware here, we have a Microchip PIC18F4550 microcontroller. Here we have a basic LCD. This is a 20 by 2 that is 20 characters on 2 lines. As you might be able to tell, I'm operating this in 4-bit mode. Over here we have a Nintendo Wii Nunchuk. This is not your average Nintendo Wii Nunchuk because this is a Chinese knockoff. As such, there are some special initialization routines I have to go through to make it work. If you look out on the internet, you might find some code on how to use a nunchuk with your microcontroller. I should warn, however, that that works for the authentic Nintendo Wii Nunchuk. Being a knockoff, there are some special routines. Over here we have a little breakout board for the Nintendo Wii Nunchuk called a Wii-Chuck. It allows you to break out the connectors on the Nunchuk connector to basic breadboard pins. You have your I2C data and clock, as well as power and ground. Now, for the purposes of this demonstration, I'm going to be running this off of a single 5-volt source. While the Nunchuk likes to run at 3.3 volts and the PIC likes to run at 5, that creates a problem. So what I've done is I've used 2 diodes here to basically drop the voltage down from 5 to about 3.6, which is close enough to 3.3. Right next to these diodes you'll see the level conversion circuit. I have just 2 basic 2N7000 NMOS transistors. Over here, here's my programmer I use to program the PIC. This is a PIC18F clone. I usually use it to power the unit as well, but as I mentioned, I'll be running this off a single 5-volt source. So let's take a look at this and power it up. Run through quick initialization, and there is our data. Now the Nunchuk features a joystick, a 2-axis joystick, 2 buttons, C and Z, and your 3-axis accelerometer. Here we have SX and SY, which indicate the X and Y coordinates of the joystick. C and Z indicate the status of the 2 buttons. Your AX, AY, and AZ indicate the accelerometer data. Now the joystick, both axes only offer 8 bits of precision. The accelerometer axes do offer 10-bit data, but here I am neglecting the bottom 2 bits. So looking at the top left, we have SX is 128, SY is 129, which indicates the joystick is currently centered. It is in between 0 and 255. The accelerometer is currently at a few values. We'll see that change in here in a little bit, and the C and Z buttons are not depressed. So let's take a look at the Nunchuk. If I pick it up and hold it about center, you can see the AX is about 128, the AY is about 128, and your AZ is about 187. It peaks at about maybe 190. So you can see, if I rotate the Nunchuk to the left, your X-axis of the accelerometer data decreases down to about 80. If I rotate it to the right, it increases about 183. Center it again, and it's back to where it was. Same with the Y-axis. If I tilt it this way, it decreases. If I tilt it forward, it increases. And if you look at the Z-axis, if I were to flip it over or even rotate it, it decreases to about a minimum of about 80. Taking a look at the C and Z buttons, up here is the C button. You push it, and it goes to 1. The Z button, push it, and it also goes to 1. Taking a look at the joystick, if I move it to the left, the X decreases. To the right, X increases. Up, Y increases. Down, Y decreases. And any combination of both here, upright, about maximizes both of them. So as I mentioned, this is a quick demonstration of interfacing a Nunchuk with a Microchip PIC. It's important to note that there are special initialization routines for a cheap knockoff like this. but don't be deterred. So that's all for this